howdy. This is Mr. Potter. We've just spent all of Chapter 3 learning how to find the derivative functions for all manner of functions that we're given. Trigonometric, inverse functions, exponential, logarithms, basically every function that we've learned along the way in our algebra and pre-calculus classes. We now know how to take the derivative of. And we can take the derivative pretty much no matter how complicated the function is. We can deal with compositions of functions, products and ratios of functions. We can even deal with functions raised to a functional exponent. So what we're going to do in Chapter 4 is we're going to talk about a lot of the practical real-world applications for this derivative function that we've learned so much about. And so today we're actually going to be talking about absolute and local extrema. So I need to start first by talking about what I mean when I talk about extrema. So for our purposes, f of c is an absolute extrema, or an absolute max for f of x if f of c is greater than or equal to f of x for all x in the domain. In other words, I know that I'm dealing with an absolute maximum if this is the highest point in the domain of a function. Now, if I look at a function like y equals x squared, obviously I'm not going to have an absolute maximum, because no matter what happens, this function is going to increase without bound. But I could say that I have an absolute minimum for this function, because I could say that an absolute minimum would be where f of c is less than or equal to f of x. So if I say that f of c is an absolute minimum for f of x, if f of c is less than or equal to f of x for all x in our domain. So in other words, I could say that this function has an absolute minimum at x equals 0, or the point 0, 0 is an absolute minimum. But because of this increasing aspect, I'd say that I have no absolute absolute maximum. And so I mention this because we're going to be talking about how to find the absolute minimum or how to find the absolute maximum. I specify this equality here because I could have a function like y equals sine of x, a function that's periodic. So this function hits the value of 1, and then we'll hit the value of 1 again, and it'll keep hitting that value of 1 an infinite number of times. So the thing is, 1 in this case is my absolute maximum value. That's my absolute maximum for this function, because it's greater than or equal to f of x for all x in its domain. So these are absolute max. And similarly, this is going to be an absolute min, as will be over here, as will be over here. In fact, I'll have an infinite number of absolute minimums. And if I try an even more simpler function like y equals 2, when I graph that function, I'm going to have a horizontal line. And so that means that not only is 2 an absolute maximum, but 2 is also an absolute minimum, because it satisfies for both of these functions. So one thing to keep in mind is that when I'm talking about an absolute max, or I'm talking about an absolute min, I'm not talking about one point in particular, but I'm talking about all of the places where a function attains that maximum value, or all of the places in our domain where f of x attains the minimum value. So we have this idea of extrema, and all of the functions that we've talked about here are pretty much continuous functions. And as long as I say that I've got a continuous function, I'm pretty sure that I can find a maximum or a minimum value. So what we're going to say is, if f of x is continuous on a closed interval from a to b, then f of x attains its maximum value and minimum value for some point on that domain, A, B. So, a couple of things I want to talk about here. First of all is this continuity. If I have a place where I've got a function like this, and then a function like this. I can't say that there's a maximum value for points in this domain. I can't say that happens. So I need that idea of continuity. The second thing is I make the very clear delineation that these have to be closed intervals. Because if I was to look at an open interval, like an open interval parabola, say a parabola from open interval from negative 2 to 2. This is continuous on that domain, but I really can't say what the maximum value is. Is it at negative 1.9, or is it at negative 1.99, or negative 1.999? I can get arbitrarily close to this value. I can just never reach when x equals negative 2. So I've got a clearly delineated absolute minimum, but because of the openness, I don't have the absolute maximum. I need continuity, and I need a closed interval in order to actually be able to say this function has a max, this function has a min on my domain. So this is our extreme value theorem. The idea is that if I have a function that's continuous, and it's continuous on a closed interval, there's got to be a high point, and that's going to be my absolute max. And there's got to be a low point, and that has to be my absolute minimum. Now, another thing that we have to deal with would be what we would call a local extrema, or a relative extrema, as some books will call it. In other words, it's not the highest point in our function, but it's the highest point around. A local extrema, we'd say something like f of c is a local max if f of c is greater than or equal to f of x for all x in some interval including c. So f of x is a local max if f of c is greater than or equal to f of x for some interval that includes c. Notice I don't have to be on a closed interval. I don't even have to be on the entire domain. There's just some spot where it's the highest point around. And similarly, I can talk about a local min as long as I specify that f of c has to be less than or equal to f of x. And there is a particular example that I could talk about. I could talk about y equals x cubed minus x. This function has three solutions, one at -1, one at 0, and one at +1. And it tends to have this type of behavior. And so I notice that I don't have an absolute max because this function increases without bound. And I don't have an absolute minimum. This function decreases without bound. But I could say for this point right here, whatever that x coordinate is, this is the highest point for some interval that includes that point. So this would be a local max or a relative max. And similarly, this point down here is really the lowest point for some interval including this point in my domain. So for this point here, I would call this my local minimum. So I can talk about local extrema. I can talk about relative extrema. Because I can talk about what's happening just in some neighborhood of that point. Just in some interval that includes that point. And if I'm the highest around, if I'm like the top of a hill, I can be a local maximum, even if there is a mountain fairly close. Even if I'm going to increase without bound at some point on my domain. So we have the distinction between absolute extrema, which is the biggest y value, or absolute minimum would be the smallest y value, or local extrema, just the highest or lowest for some interval. And so I want to talk about what this looks like from a picture. So I'm going to draw a picture of some esoteric function. I have no idea what the equation of this function is. But I know that I'm going to start here. I'm going to come down. I'm going to go up. I'm going to come down here. I'm going to go like this. And I'm going to come down and have an open spot here. So looking at what I have here, first, this is my highest point around. So this is an absolute maximum. For this particular C, though, I can't really call it an open interval about that point because my function's not defined. So some books argue about this. Our book in particular says that this is not a relative max. And you can argue about that, whether or not that is an absolute or I mean, whether that is a relative max. You can't argue with the fact that it is an absolute max, because this y coordinate is the largest y coordinate for any point in my function. It's higher than this point over here, this point over here, which would be a relative max, because for some interval including this point, it is the highest point around. And so I could say I have a relative max here as well, because at this point, for any interval containing, for some interval containing this point, it's going to be the largest point around. But neither of these points are absolute maxes. Similarly, I could call this one a relative min, because for some interval containing that point, it is the smallest around. But I would say it's not an absolute min. And similarly, this cusp down here is also a relative min, but it's not an absolute min. And in fact, because this is an open interval, I can actually say that this function has no absolute minimum, because there is no lowest point on this function, and that's due to this open interval that I've got on this side, this open point. So this is just talking about some of the situations, and I'm noticing a couple of things here. One of the things that I'm noticing is that when I'm talking about relative extrema, relative extrema either occur when I've got these horizontal tangents, or where I have these vertical tangents, the places where my derivative is undefined. And similarly over here, I've got this corner where my derivative was not defined. So that means that having a relative extrema, a relative max, or a relative min really is dependent on the derivative. And so what we're going to do is we're going to introduce a term called the critical point. So a critical point is a point where the derivative is equal to 0, or the derivative is not defined. The critical point is a point where f prime of c is equal to 0, or f prime of c is not defined. And one thing I need to make perfectly clear is that a critical point is a point. In other words, I have to have an x coordinate and a y coordinate. If I'm dealing with an x coordinate and y coordinate, some books will call just the x coordinate a critical value. But on the AP exam, if they ask for a critical point, I have to give a point. That's really a key here. So what I'm going to be looking at is I'm going to be looking at where my derivative is 0 or where my derivative is not defined. Because relative extrema occur at critical points. Okay, relative extrema occur at critical points. Now, I am not saying that every critical point will be a relative max or a relative min. I'm just saying that if I have a relative max, it has to be at a critical point. If I have a relative min, it has to occur at a critical point. So then the question comes back to, well, what about when I'm dealing with absolute extrema? And so when I go back to my case over here, I could have had an absolute extrema somewhere on this domain, but it would have been either at a high point, like where the derivative had a horizontal slope, or at a cusp or a corner where the derivative was undefined. But I also have to include these places here where the derivative may not have a value. I may only have a one-sided derivative because we're dealing with a boundary point. So when I'm dealing with absolute extrema, absolute extrema will occur at critical points and boundary points. Not and, or. So when I'm dealing with critical points, they're going to occur, I mean, when I'm dealing with absolute extrema, they're going to be critical points or boundary points. So then our task is, if we're looking for extrema, our first task is to look for critical points. So I want to take a look at one particular example. I want to take a look at y equals x cubed. And the reason I bring this up is because there is a place in the domain where the tangent is equal to 0. Because I know that the derivative would be 3x squared. And if I set that equal to 0, trying to find a critical point, I get x equals 0, or the point 0, 0 would be my critical point. However, this is not a relative maximum. It's not a relative minimum. I can tell that by inspecting the graph here. And later on, we'll talk about more analytical methods to determine when we're dealing with a relative max or relative min. For right now, though, I can tell by looking at the graph, it doesn't satisfy the definition of a local extrema. It's not the highest y value on some interval, including the origin, and it's not the lowest point for some interval containing the origin. And similarly, because my domain and because my range is unbounded, I also know that it's not an absolute extrema. Because there is no highest y cubed value. There is no lowest y equals x cubed value. So I'm not dealing with the relative max. I'm not dealing with an absolute max. And so the thing is, on the full interval from negative infinity to infinity, I have no absolute or relative extrema. What's more interesting, though, is what happens when I take a look at this on a restricted domain. Let's say from 1 to 3. And as soon as I make this a closed interval, just by putting those brackets on, because this is a continuous function on a closed interval, I'm guaranteeing that there's got to be an absolute maximum. And I'm guaranteeing that there's got to be an absolute minimum. So I've got here at x equals 1 and at x equals 3. So somewhere on this domain, I've got to have a absolute maximum. I've got to have an absolute minimum. And just by looking at this graph, I notice, yes, I do have an absolute maximum. My absolute maximum occurs at the point 327. And my absolute minimum occurs at the point 1, 1. But I have no relative extrema. Remember that relative extrema can only occur at my critical point. Well, the problem here is that my critical point is not in my domain. And so for this particular graph, I do not have any relative extrema. So let me go ahead and get a different domain up here. Let's say I'm dealing with the domain from negative 1 to 1. Again, as soon as I close this domain off, the extreme value theorem holds, and at some place in that closed domain, I have to attain my maximum, and I have to attain my maximum, my minimum. So I have an absolute maximum at the point 1, 1, and I have an absolute minimum at the point -1, -1. But even though my critical point is now part of my domain, nothing here is happening. I had a maximum at x equals 1. I had a minimum at x equals -1. But for this point, there's no interval around that point that I can choose. There's no interval I can choose such that the origin is higher than any point in that interval. And there's no interval around the point 0, 0 that I can choose where the origin is the lowest point on the function. So I have no relative extrema. So we've taken a look at this y equals x cubed. There's a couple of more examples that I want to take a look at. So I want to take a look at y equals the absolute value of x. So let's talk about it first graphically, and then we'll start talking about it analytically. So I know that the graph of y equals the absolute value of x looks like this. It's our V graph. And so just looking at this graph, I know that I'm going to have no absolute maximum. That's because my range is unbounded going towards infinity. But I do see that I have an absolute minimum at the point 0, 0. That is the lowest possible value on my graph. If I'm looking at relative extrema, I have no relative max. And again, it's because for any point that I choose on this V, I can't say that for some interval it's the highest point around. But I could say that I have a relative minimum at the point 0, 0. Because for the origin, if I choose any interval that includes the origin, then I'm going to have the origin be the lowest point around. For every point to the left of the origin and every point to the right of the origin, y is greater than 0. So this is looking at it just from a graphical standpoint. So what I want to do now is I want to take a look at it from an analytical standpoint. And of course we said that absolute extrema occur at critical points and boundary points. So looking at this, I've got this function, and I know that my derivative is piecewise. I know that for all x greater than 0, my derivative is 1. The slope of this part of my graph is 1. And for all values of x that's less than 0, my derivative is negative 1, because that's the slope for all values of x less than 0. But if x is equal to 0, my derivative does not exist. Does not exist because the left-hand limit and the right-hand limit aren't the same. It does not exist because my graph has a corner at that point. And a critical point is where the derivative equals 0 or where the derivative does not exist. So notice that because 0 is in my domain, but the derivative does not exist, the point 0, 0 is a critical point. And so that means absolute extrema has to occur at critical points and boundary points. Our graph has no boundary points because there's no boundary. There is no restriction of my domain. The way that I've graphed this function, my domain is all real numbers. So I've looked at critical points, I've looked at boundary points. There's only one possible point. And of course, looking at the graph, I know that this possible point that I'm talking about is an absolute minimum. Now, I know that's what happens when I'm dealing with absolute extrema, but if I'm dealing with relative extrema, I know that they occur only at critical points. So the only thing I have to look at is the critical point, and the only critical point I have is the origin. So when I look at this, I'm looking at this critical point. It can either be a relative max or a relative min, or neither, because just because it's a critical point doesn't mean it has to be a relative extrema. But looking at the graph, I notice that this is a relative min at the point 0, 0. This is one way to look at it, and of course here I'm using the piecewise definition of the absolute value. I know that it's equal to x for all x greater than 0, and I know it's equal to negative x for all x less than or equal to 0. And I know that whenever I have a piecewise defined function, I could have the derivative not exist at the places where the domains meet. That's one of the things that we learned when we were talking about continuity and differentiability. So I want to take a look at a different piecewise function. I want to look at this piecewise function where I've got y equals this defined function. I've got negative x squared minus 2x plus 4 for x being less than or equal to 1. And I've got negative x squared plus 6x minus 4 for x greater than 1. And again, if I want to look at this function, I need to look at it from the context of critical points and boundary points. Now, just looking at this, I don't have any boundary points because I have no restriction of my domain where a point is not in the domain. So I'm not going to have to deal with this boundary point issue. What I will have to deal with, though, is this critical point issue. Remember, critical point is going to be where my derivative equals 0 or my derivative does not exist. So what I need to do is I need to take a look at these derivative functions for these domains. So for x less than 1, again, remember, I could lose a derivative at x equals 1. That's something I'll have to actually check. When I take the derivative of my function, I end up with negative 2x minus 2. And when I take the derivative for x is greater than 1, I'm going to end up with negative 2x plus 6. And so I see what's going to happen here. At x equals 1, my derivative does not exist because there's no way that negative 2x minus 2 could be equal to negative 2x plus 6. These are parallel lines. There's no place where these parallel lines will intersect. So I know that I have a critical point at the point 1 something. And if I substitute in here, I'm going to have negative 1 minus 2, so negative 3 plus 4, which is 1. And just to check that I'm continuous here, if I have negative 1 plus 6, that's going to be 5. 5 minus 4 is 1. So I am continuous at that point. So this does work with my continuity issue. But I also have two other situations here. I have the situation where I could set this expression equal to 0, or I could set this expression equal to 0. Because critical points where the derivative is equal to 0, or the derivative does not exist. Now, I just took care of does not exist. The only place I found where it does not exist is at this point 1, 1. Every other place my derivative is well defined. For x less than 1, it's this. Negative 2x minus 2 equals 0. So I've got negative 2x equals 2. And so x equals negative 1, which is in my domain. So I know I have a critical point at negative 1, and when I substitute it into my original function, that's going to be negative 1 plus 2 plus 4. So that's going to be 5. And I've also got this situation down here, right? I have negative 2x plus 6 equals 0, or negative 2x equals negative 6, or x equals 3, which is in my domain. So I have a critical point at 3, and substituting into my original function, that's going to be negative 9 plus 18 minus 4, which is 5. So now the question is, are these relative extrema? Are they absolute extrema? They could be neither. But if I take a look at this first part of my domain, for this part of my graph, I know that this is a parabola opening downwards. So I know I've got some type of parabola that's opening downwards. And similarly for here, I've got a parabola that opens downwards. Now, I know that I reach 5. I know I reach 1. And I know that I'm going to reach a y value of 5. So I really got this M shape going on here. And so looking at what I have, just from the fact that I know how my parent functions behave, I know how the transformation of my parent functions behave, and I know these critical points. These critical points have to be the places, the only possible places where I could have extrema. I noticed that 5 ends up being my largest y value. So these are both absolute maximums and relative maximums. So they're absolute maximums because they are the largest y value around. There's no other place where I can get a y value that's larger than 5. And they're also relative maximums because I know for any interval that includes negative 1 or that includes 3, those are going to be the largest y values on that domain. And at this point here, this point 1, 1. I know that this point here is a relative minimum. So I have absolute max. I've got a relative max. I've got an absolute min and an absolute max and a relative max. For both these points, negative 1, 5, and for 3, 5, they're absolute maximums and relative maximums. For 1, 1, I know that this is a relative minimum. And my graph is going to have no absolute minimum. And that's simply because my range is unbounded for negative values. My range is going to extend down towards negative infinity. There is no absolute lowest y value. So we're going to continue talking about this idea of finding critical points and using critical points to determine whether I have maximums or minimums, absolute or relative. So this is Mr. Potter. Thank you for watching. Have a great day.